All right, so welcome back. Hope everybody is doing well. Beautiful, glorious day here, which is surprising for this time of year, but definitely feeling spring. So, any questions on anything so far? What distro do I use? That's a really good question. I think it's Ubuntu 18.04, and I'm using XFC mostly for my desktop, but a little bit of KDE mixed in here and there too. Um, I upgrade when, the long-term support is no longer supported, but other than that, I don't really think too much about it. So, I could be wrong. Cool. Other questions? I'll take questions on anything. All right. Well, um, let's continue what we started, which was looking at implementing linked lists, kind of barehanded. So we have a linked list class in Java that does most of what we need to do, but I want to go through an example of how we would implement linked lists ourselves. Not because we need to do that today or this course, but just as an example of a relatively simple data structure, at least for us now, relatively simple, a linked list, something we've worked with extensively, cobbling that together into our own Java class. And we're doing this as a preamble to working with implementing our own trees. And PA3, I'm probably going to make a decision tree problem. Decision trees being a kind of binary tree, they're not binary search trees, but they have a similar structure to BSTs. So knowing how to implement those is going to be part of PA3. So we want to be able to leverage what we know about these data structures from 222 to implement them in Java. So we're going to start with linked lists, and this is therefore mostly just an example, a way to kind of ease into this. So if we have a linked list class, let's call it a my list. And mostly what we need in our list is just a reference to the list itself, right? So an empty list, we're not going to do Sentinel nodes, okay, just because. So an empty list is a list that has no nodes. Okay, a list with one node has just a single node. A list with two nodes has two nodes where the first one points to the second, and so on. So we're going to define a node class. And so in the MyList class, mostly we're going to have a node, which we'll call, let's just call it header. And this is the first node. Or if there is no first node, it's just going to be null. Alright, so we started building up a node class yesterday, so let's go with integers. I did strings this morning, so let's have integer data, and let's have a node that we call next. Alright, so let's make an add method. So it doesn't have to return anything. Let's take an integer num, and let's add that to our linked list. And then let's make a print method, which will go through our list and just print it out, say one number per line. Now our node class doesn't really need to do a whole lot. It's mostly a data class, right? It has the pieces of data corresponding to a node. but we'll probably go ahead and build a constructor, because a constructor will let us make these things private. And let us put some control over how we update these, so we could make a mutexer and an accessor, right? I'm probably not going to worry about that for now. But you could put, levels of control on this. Alright, so our constructor, usually when we create a node, we are creating a node because we have a piece of data we want to insert into our linked list. So we're going to make a constructor that takes an integer. And all we're going to have to do is store that integer into the data field of the node. We'll probably set the next field to null just to give it a known value. And that's pretty much going to be our whole node class. So let's go ahead and implement some of this in Java. Okay, so the usual drill that we've seen before. So our node class has two fields to it, a data node and a next node. And that's it, right? So it's kind of like a struct node, just held two fields. And this does not trip it up, right? Defining that a node contains a node inside it, that's okay, because these are really references to nodes, okay? So they're basically pointers, but we don't use the pointer word in Java. So let's make a simple constructor. Which we construct just by passing the value that we want stored in the node. And there's our whole constructor, and the next equals null is redundant because it would be null by default, but let's be explicit about it anyway. So this is just creating an empty node that looks like this. It's got D in the data piece, and it's got null in the next piece. Okay. And I think that's our whole node class. So compile that. Wow, we made like 4 lines of code and we got a zillion errors. Whoa. Okay, that was sketchy, but we're back. So, alright, so there's our node class, and we're done with this, okay? So I'm going to close this file. We're not going to have to open it again. We're not going to have to compile it again. We're going to think of this like a string or a rectangle or an even number, right? It's a thing that we can use anytime that we want a node. We can just construct a new node, and it'll be an object of type uppercase node, right? So encapsulation, right? We're putting all the stuff inside here. And it's a thing, it's an object. So let's make our linked list class. Alright, so inside our linked list class, we need a reference to the first node. So let's set this up, call it header. So this is either the first node of the list, or null if the list is empty. Alright, that's our handle to the structure. Okay, let's make a method to insert into our list, and let's insert in the correct order. So we'll do increasing order. So we're not going to return anything from this. We're going to assume it does not blow up, and if it blows up, it'll just throw exceptions, and we'll deal with it. But other than that, there's nothing we need to get back from the add method. Okay, we could return, I don't know, something that tells us where we added it in the list maybe. That would be useful, I don't know. But we'll just make it void for now. So void, make it public. Add, and we'll just add integer d for data. Alright, so first we need a new node containing d. So we can say new node equals new node parentheses d. Okay, that's doing the malloc. It's checking to make sure the malloc worked. It's setting the data field equal to d. It's setting the next field equal to null. Okay, we get all that for one. And somewhere in our documentation for the node class, we've described what this constructor does and said, you know, this builds the object and sets the data and next field accordingly. Okay, so that's the node that we want to insert into our list. So let's look at linked lists without sentinels. Alright, there's one kind of linked list. Here's another kind of linked list. Here's another kind of linked list, which is totally empty. Okay. There's edge cases we need to worry about. So the first edge case is when the list is completely empty. If we want to insert it into an empty list, it's not going to work with like the rest of our code. So let's start with some edge cases. So edge case 1, the list is empty. In this case, new node becomes the node of the list. Okay, how do we know if the list is empty? If header equals null, set header equal to new node, and return. Alright, that's one edge case. So that deals with the empty list. Now having a single node is not necessarily an edge case. But let's put some values in here. Let's put in 5, 10, and 15. And up here, let's put in 1, 2, 5, 10. And suppose we're trying to add a 4. So we're going to make a new node. Whose data value is 4. Well, so in this case, we need to insert before the first node. We need to put our new node right here. And that is an edge case. Because normally what we're going to do is we're going to travel down the list until we find where to insert our new node, and then we're going to adjust that previous node's pointer. Okay? But if we're inserting right in the very beginning, that's going to change the header of our linked list. Okay, here header is pointing to 1. After we insert a 4, header is still pointing to 1. Here header is pointing to 5. After we insert a 4, header's got to be pointing to this. So that's a fundamentally different case. So this is a new edge case. Edge case 2, insert before the header node. So let's see if that's our condition. We've already made sure the header exists, right? If the header didn't exist, this would have fired true and it would have kicked us out. So let's see if we should insert before the header node. So if the data we're inserting is less than header dot data, right, which would be get data if I was hiding my information. So if D is less than the header's data, yes, insert new node before header. So header dot next equals, sorry, new node dot next equals header. So that says our new node's next field should point to header. Right, this is header right now. And then what do we want to do? Change header to point to our new node. And then return. So we change header to point, change new node to point to the header, change header to point to our new node, and we're done. We've inserted a new node in the beginning of the list. And when we look at the header object, it will correctly point to that first node. Okay, and notice I'm not using else's here, right? I'm returning from inside this if statement, so I didn't need to say else. I'm returning from inside this statement, so I don't need to say else. Anytime I say else, I would have to indent further, right? Consistent indenting. And so my code starts getting more and more deeply nested, and your debugging becomes that much trickier, and so on and so forth. So if I can exit from my method, I'm going to do that. And now, when I'm at this location, we just want to loop until we find the right spot to insert the new node. Okay, so what does this loop look like? Well, let's say we're inserting a 4. We're going to make a temporary pointer. So this is header. We're going to make a temporary pointer. And we've done this before with pairs of pointers, previous, next, previous, next. I'm going to do this with a look ahead instead. I'm going to use one temporary pointer. And I'm going to say, should we insert before the node that comes after this? In other words, should we insert right after temp? So we look at a 4, what do we have to do? We have to compare it to the value of the node after temp. And 4 is bigger than 2, so we're going to say, no, let's not insert after temp. So we'll change temp to be the next node. And we'll say, should we insert right before the node after temp? Well, the next node has a value of 5, 4 is less than 5. Yes, we should. And because we're sitting on the node we want to insert after, now it's very easy. We simply take our new node and point where temp is pointing, and then we change temp to point to our new node. And we've done our insert, 1, 2, 4, 5, and so on. So let's turn that into code. And when does this end? If we keep moving down and we get to where temp is here and there is no next node, right? So the guts of our logic is going to be something like this. If temp next dot data is bigger than D, then we want to insert right after temp. In other words, between temp and temp arrow next. I can't believe I'm writing arrows. There we go. You didn't see that. So if temp next, the next node's data field is bigger than what we're inserting, insert right before temp next, right after temp, so in between. Okay, but if I keep going and temp next becomes null, this is going to blow up. Because if temp next is null, temp next data is going to be a null pointer exception. So we want to make sure that temp next is not null, but we want to keep marching down this loop. So this defines the structure of our while loop. So while temp next is not null, so as long as there's a node after temp. And we need to seed this process by starting off at the header. So temp will be the next node that we might want to insert after. Let me get rid of the word next. Temp will be a node we might want to insert after. Okay, so as long as there is a node after, let's see if that node's data value is bigger than D. And if it is, what are we going to do? Insert right after temp. So new node next equals whatever temp is pointing to. And then temp should point to new node and return. So that inserts temp in between our new node in between temp and temp next. Otherwise, you got to move down the list more. So temp equals temp.next, and there's the end of our while loop. And again, you know, I put an else in my comments here, but I did not put an else in my code. If I had, my code would look like this. Well, that's not horrible, right? But this is at the same level as this. And I've got, you know, my double brackets here, and you always run this risk of like getting an error about brackets, and it's too easy to just start putting brackets in where it says there's an error, and suddenly your code is totally like munged up, right? So by doing this, right, by exiting out of my if statement here, so I keep my indent level to just one indent, right? I have a while loop. I'm doing an if, I'm doing an assignment statement. I'm doing two things in my loop. I just think of this as one thing, right, which might happen if I'm at the point where I want to insert. Otherwise, I do this thing, which is move down the list. And my whole thing is just sort of a single, you know, level of indenting for my while loop. I don't know if that makes sense, but that's just kind of like, you know, stuff you pick up along the way. Maybe it's helpful. If you got your own way of doing this, that's cool. Alright, so this should loop until it finds the right place to insert, unless we come out of the loop. So if we get here, we ran out of nodes. What does that mean? We never found a node that was bigger than our new node. So new node should go on the end of the list. And when we come out of here, we're coming out of here because, you know, temp was right here, and temp next was null. So when we exit the while loop, temp is the last node of the list. So we want to insert new node right after temp. That's all you need. And we can return right there. We could say return, or we don't have to, because we hit the end of the method, it'll return automatically. So there's our add method. And let's see how we're doing on syntax. Not bad. Oh, and I was bragging about how you can keep your brackets straight, and I messed up my brackets somehow. I'm apparently tired today. Alright, so that's the end of our while loop, so we still need to end our method. Ooh. Okay. All right, I'm back. Yeah. So there's our while loop for moving down the list. If we come out of the while loop, we're at the end of the list. Keep moving down the list. Temp equals temp next. Okay, here we ran out of nodes, so new node should go on the end of the list right after temp. So set temp equal to set temp to point to your new node, and that's the end of the add method. I planned this because I wanted to show you how to debug, right? No, not really. So I'm going to compile, but I'm going to pipe with an ampersand to send standard error through more so I can look at my first few errors, since apparently I'm going to make a lot of errors right now. And my first error is line 13, new node equals new node. So let's look at line 13. I forgot to tell it what kind of thing new node is. So it's a node. I'm gonna close my window because they're finishing up. Alright, so let's recompile. And line 28, can't find the symbol. So I'm doing a 28 and an uppercase G to jump down to line 28. And so I need to declare temp to be a node. So let's do that, and let's recompile. And hey, we lucked out here, so let me get rid of that pipe. Alright, so we're back in business. See, it's easy. Alright, let's write a print method so that we can examine the contents of our list. So, print the contents, one number per word. See, I've been trying to correct my typos without making them, and I think that's throwing off my mojo. So public void print. So let's make a temporary node that's equal to the header, right? So we'll just start off a temporary right here. And there's no edge cases here. We can just say, well, temp is not null. We'll print out temp's data and move down the list. So let's just print temp.data. And then set temp equal to the next node, and do that until temp is null, and that's the end of our print method. Alright, so that compiles without errors. So that's probably a complete, basic linked list class that lets us construct add and print. So we could put in search and delete and all that kind of stuff. But let's just play with this a little bit. So let's make a main program, and let's do mylist errors equals new mylist. Right, so we'll go with the flow. So errors is a linked list, right? And let's add some numbers. All right, and then let's see if they got added in the correct order. All right, so this is just a dummy test bed program, right? Just sort of exercising the code, see what it does. If it's working correctly, we should get our numbers coming out in the order, you know, in numeric order, despite the order we put them in. So let's compile that. Let's run it. And looks like it actually worked. Okay, so we built a linked list containing all of these items, and they got moved around and inserted in the correct spot. Okay, which is kind of cool. So the goal here was, you know, to show how easy this is, which apparently it's not as easy as I thought it might be. But, you know, the real goal is to take what we've done in 222, data structures in C, and sort of see how that translates over to writing in Java. And it's not, you know, a step-for-step plug-in replacement. I don't want it to feel like that. But I want you to think about the concepts, right? What does it mean to have a linked list? What does it mean to move down a linked list? And to, you know, have an idea of how we can, you know, do similar things in Java. And the syntax hopefully is a little less quirky than it might have felt in C, right? We don't have to specify this is a pointer or the thing pointed to or do mallocs or stuff like that. It's like, well, temp's next node is not null, right? I mean, that's really what this says. Well, temp's next node is not null. If temp's next node's data is bigger than D, then set new node's next node to be whatever temp's next node is, and then set temp's next node to be new node, right? Well, if you're playing along on your scorecard and you're drawing pictures, right, that's exactly doing this thing, right? So the goal is to be able to, you know, you have some intent. You can describe on paper what it is that you want to have happen. There's no Java on here, right? And then you can write code to say do those things, right? And that's sort of what this block is right here, for example, is inserting or moving down to the next thing. Or in the print, you know, saying, well, we have a node, print out its data value, go to the next node. All right, so let's take this a little further. Let's print out the linked list by concatenating to a string and just using print line. And of course it just gives us, you know, the name of the class, @ sign, and then some internal reference. It's not what we were hoping for, right? We were hoping for a nice collection of numbers with spaces in between them or something like that. So we can write our own toString method. So public string toString, which takes no arguments. And remember, you know, whatever toString returns, that's what will get concatenated. So now our linked list is just haha, and it's always going to be haha, because that's what the toString method returns. Okay, so we could make this something a little more reasonable. So let's make our output string equal to an angle bracket. And let's just rip off this code from up here and say node temp equals header. And then while temp is not null, instead of printing temp.data, let's set output equals to output plus temp.data plus a comma. And then move down to the next node and iterate over the whole linked list until temp is null. And then let's put our closing angle bracket on the end. And let's return our output string. So we're using the same code we do traverse to print out, but instead of printing anything, each time we get to a new node, we're just concatenating its data to an output string with a comma at the end. And this will almost be glorious, right? So there's our list, and it looks nice, except, you know, there's always the annoying trailing comma at the end. So how do we get rid of that? Well, we could put the annoying comma in the beginning. And now it's great, except we have an annoying leading comma in the very beginning. Well, that's easier to get rid of because we know right away when we're at the beginning. We don't know when we're at the end until we go to the next node. So, you know, I could have said if temp next is not null, put a comma on the end. But let's just do something in the beginning here. Let's say if our output is equal to a less than sign, output equals output plus comma plus temp.data. Sorry, if it's equal to a less than sign, let's just do output equals output plus temp data. Else, let's set output equal to output plus a comma plus temp data. So now we've suppressed that leading comma. And again, there's a lot of ways you can do this, right? I could have said if output, if not, output equals that. Let's set output to equal to output plus a comma. And then let's set output equal to output plus temp.data. So we're doing one extra line in the beginning just to concatenate a comma if we're not in the beginning of our output string. Right, and that works too. Or we could use a ternary operator and say see if output is equal to a less than sign, and if it is, concatenate an empty string, otherwise concatenate a comma. And now we have basically a single line solution. Set your output equal to the current output plus either an empty string or a comma plus the data value. Ooh. Extra parentheses, right? And so there again, we've suppressed it. Concatenation is a little finicky sometimes. You have to make sure it understands that what you're trying to concatenate is, you know, what you actually want to concatenate. So extra parentheses there. So yeah, different approaches, but you get the idea, right? And I'm showing you these different variations just to sort of like, you know, reinforce the idea that like you get to do this how you want, right? I'm not going to tell you you have to do things in this particular way or that particular way, right? Other than commenting, where I'm telling you, you know, you need to have comments here and there and so on, and style, where I'm saying you have to have a consistent style, but you can pick what that style is. And you can choose, you know, whether you're going to test for positive conditions, negative conditions, use a ternary operator, use an if-else, etc., etc. So enjoy that freedom, right? It's part of the fun of programming. All right. Any questions on linked list implementation? You know, or the takeaways from that? So I want to go on to trees. So trees, right? Those were the structures we did after lists. They have a similar node structure. So we have a piece of data. Let's say it's still an integer. And we have a node which we call left. And we have a node which we call right. And we want to stick with recursion, right? Recursion is the easier way to deal with most of our tree operations. So insert, search, traversing, those things have very natural recursive algorithms, right? When we want to traverse a tree, we traverse the left subtree, we print the root data, we traverse the right subtree. Remember that? So here's the one kind of odd thing about implementing things like trees. We can make a class called tree. And the main thing we need in here is the root, right? So the root is going to be a node. And the root starts off null. And when we want to traverse a tree, right, suppose the root is not null, what we really want to do is first of all say, does the root node have a left child? So we'll say if root.left, right, so if root is null, just return, right? So this is our traverse code. So we're slipping into pseudocode really quickly. If our root is null, let's just return. Otherwise, we're going to say something like, if root.left is not null, then traverse root.left, right? Or maybe root.left.traverse. All right, because we're doing objects. Well, here's the thing. Root.left is not a tree. Root.left is a node. So this traverse method has to be inside our node class. So inside class node, we're going to have traverse and insert and search and so on. But the user, the main program, doesn't want to think about nodes, they want to think about trees. So in our main program, we want to say something like tree t equals new tree. And then we want to say t.insert 5 and t.insert 20 and t.traverse and so on. Right? The main program wants to deal with this tree object, but the code for doing that is actually part of the node class. And why can't the main program deal directly with nodes? Because you end up doing something like this. You have to know the first time that you're inserting that you don't already have a tree. And you need to do something here like node t equals new node 5. And then when you want to insert a 20, you just say t dot insert 20, and so on. But if I delete some nodes, I need to know if I've deleted my last node so that when I want to insert into my empty tree, I construct a new node instead of trying to call insert. In other words, I'm managing the root myself, and we don't want to do that. We really want something like this. Construct a tree. This is the root of my tree. Let me insert, let me traverse, let me do that kind of thing. Maybe my tree is empty. I don't care. I just want to use t, right? That's my handle to my tree, not necessarily the root. So inside the tree class, we're going to find methods for traverse and add and insert and search and so on. And those are just going to be wrappers or front ends to the methods in the node class. So that's a little weird, but once we code it up, I think it'll make good sense. Basically, because we're doing recursion, we want to be able to call, say, an insert method or a traverse method on the fields of a node, right, the left and right children. These need to be methods inside the node class. But because we want the outside user to not have to think about nodes, because their tree might not have any nodes, we want traverse and insert and search methods in the tree class. But they're really just going to call these methods as methods from the root node, right? Or just do something special if the root happens to be null. So if we keep that in mind, coding this up is really, really short, right? Because we can do recursion for things like insert and traverse. We don't really have to think very hard. We don't have to keep pointers and move through lists and compare things and so on and so forth. So we'll code this up tomorrow. And this will be, an example of coding up a binary search tree. PA3 will be doing a different kind of binary tree called a decision tree. So the code for that will look different from this, but similar idea. Okay, so that's our plan for tomorrow. So keep working on PA2. Let me know if you have questions or issues with that. And code up some lists if you feel like it, or code up some other data structures. Or go outside and enjoy the day, or do all of those. Do some coding outside. All right. Have a fantastic afternoon. I will talk to you tomorrow.